Hello, this video is going to be about impulse, which is momentum in motion. When two objects transfer momentum, they do so with something called an impulse, and that's the focus of this video. So you maybe have seen somebody play pool before, right? You hit the pool balls with a cue, and you can use those to hit other balls, and they bounce around the table. Let's think about where the momentum is moving in this particular movement, where the guy uses a cue to hit this ball, to hit that ball, to go into the pocket. Let's think about what's happening. So first, the arm right here is going to give the pool cue some momentum. So the arm moves the pool cue. And the pool cue has some momentum because it has some forward velocity. Then the pool cue transfers the momentum to the white ball with a collision. So the cue hits the ball and it transfers the momentum over. You can hear this in the click. You can also see it right here. Look at the end of the pool cue. It's moving pretty quickly, but then it slows down when it hits the yellow ball. The yellow ball moves forward, this thing slows down because the ball stole some of the momentum. So now the white ball has some momentum, which is why it moves over. Because now it has some velocity, because it has that momentum, it moves. And then the white ball transfers the momentum to the green ball in a second collision. You hear a click, the white ball stops moving, and the green ball starts moving, so the momentum transfers over. Finally, the green ball has the momentum and it moves into the pocket, so it moves over to the edge of the table. Now, as an aside, when it lands there, the momentum doesn't disappear. Even though the green ball stops moving, momentum is still conserved overall. So, the momentum in the ball gets transferred to the pool table, and then it gets transferred from the pool table into the spin of the planet, so it actually affects the way the planet rotates. There's a momentum transfer to the spin of the Earth. But the momentum of a pool ball is very, very small compared to the planets, so you don't really notice it. So it's unnoticeable. And not only is it unnoticeable by itself, but there are also tons of momentum transfers on the planet around the world at any time, so they mostly cancel out. This person is hitting a pool ball this way, then this person is hitting a pool ball that way, and they all cancel out in the long run. So you're never going to notice it, but every time you move something, it will affect the motion of the Earth a teeny tiny little bit. Importantly, momentum is always conserved, always and forever. So this is where we get to the focus of today. This transfer of momentum always happens through the application of a force. Click. There is a force that happens when the pool cue hits the pool ball and the momentum moves over. In fact, this was the original definition of a force. Newton's laws were not written the way that I taught you in the Newton's laws video. F equals ma was not originally written like this. This wasn't Newton's second law. Newton's second law was called, it said the force was equal to the flow rate of momentum. So the definition of a force is the change of momentum over time. That's literally the definition. If a really high force collision happens, then you transfer momentum really quickly. So if you hit the white pool ball really hard, the momentum transfers quickly. If a low force collision occurs, you have a very slow momentum transfer. So the momentum transfers very slowly from the pool cue into the pool ball. So if the momentum moves slowly, you have low force. Now, to summarize this, we say that two objects are applying forces to each other when they're transferring momentum. This is literally the same thing. The stuff we learned about before as a force, we are now relearning as a transfer of momentum. So some of these problems might seem a little bit similar. But what is the precise relationship between a force and a momentum transfer? I mean, I could tell you this, but this isn't very helpful unless we have an equation that lets us predict exactly what's going to happen. So let's play with some equations and actually get the relationship. Momentum is mass times velocity. The change of momentum is the change of momentum, the change of mass times velocity. Now, the mass of an object doesn't really ever change, but the velocity can. So the change of momentum will usually be caused by a change of velocity and not a change of mass. So the change of momentum is always going to be caused by a change of velocity, not a change of mass. So the delta really doesn't apply to the m, it applies to the v. So let me just rewrite that. So I've just figured out that this is a very good equation for the change of momentum, the mass times the change of velocity. I'm going to use this to get the equation. Now we're going to do a pro physicist move right here. This is a trick that gets used all the time in higher level physics and math classes. It might seem pointless for a while, but bear with me. We're going to multiply by the number 1. So, we have this formula, the change of momentum. That's, of course, equal to itself. And we're going to multiply by literally the number 1. Now that doesn't change anything. These two equations are still equal, because multiplying by 1 doesn't change the value of your quantity. So we're always allowed to do this because multiplying by 1 doesn't change anything. Anything divided by itself is also equal to the number 1. So if I have like 5 divided by 5, that's equal to 1. And that's not only true for 5s, that's true for every number, and even variables. So if I have x divided by x, that's also going to be equal to the number 1. And we're going to use this. We're going to substitute this equation for the number 1. The variable t divided by t is equal to 1. The t means time. So we're going to take this and substitute in an alternate version of the number 1, which is time divided by time. Because for every possible time interval, if you divide it by itself, you get the number 1. So you're allowed to do this. And now this is where the magic happens. When you multiply and divide, you can do it in any order and the answer doesn't change. Therefore, we can divide by time at any point and not change the quantity we're dealing with. Because right here, I'm doing the mass times the velocity times the time divided by the time. But if I wanted to, I could divide by the time, right here. Or I could divide by time right here. It doesn't matter where I do it. So I can move around this division by time anywhere I want, and I still have the same formula. So we can rearrange it and divide by time here, instead of at the very end. So I'm going to move this division by time over. Doesn't change our thing, we're allowed to do that. But now we have a delta v over t, and maybe you've seen this before. Delta v over t, that should look familiar, because the change of velocity over time is the same thing as acceleration. So we can substitute. Acceleration is equal to the change in velocity over time. So acceleration can go in these parentheses. And now I'm going to clean it up a little bit. We have that mass times the change in velocity, the change in momentum, is equal to mass times acceleration times time. And finally, we see something that can help us figure out a relationship with force, because we know that F equals ma. So right here, ma, that is the force. Bam. Now we have our relationship. This is the relationship that we were looking for. When force transfers momentum to an object, the change of the object's momentum is equal to the force multiplied by the time that the force acts on the object. This should make sense to you from your experience of the world. If you apply a force for a long time, the thing you're pushing will move faster. And if you apply a force for only a little bit of time, things barely end up moving, even if it's a lot of force. So imagine you're in a car, and you have the gas pedal, right? And you push it all the way down to the ground. So you push the gas pedal all the way down, the engine is applying a lot of force. If you keep the gas pedal down for a long time, maybe like 12 seconds, you'll be going like 100 miles an hour. But if you take this gas pedal and you just pump it down and then immediately move it back up, so for not very much time it just goes down and up, you will barely end up moving. I don't recommend you try this, but if you're on the highway and you just like stomp on the gas pedal, but take your foot off really quickly, you're not going to end up moving much faster. Now the change of momentum. This quantity is so important we actually give it a special name, which is what this lecture is named after. We call it the impulse. So the change of momentum of an object is called the impulse that you give the object. Impulse means change of momentum. They're just synonyms. The units of impulse are going to be the same as the units for momentum, so kilograms times meters per second, sort of a weird unit. And it can be either negative or positive, depending on how the momentum is transferred, whether you're transferring positive momentum or negative momentum, meaning you're moving something forwards or backwards. So this is our formula. This is the change of momentum, also called the impulse, and a little bit confusingly, this is sometimes also called the impulse, but it's the same thing because it's okay. So we have force times time is equal to the final momentum minus the initial momentum. The impulse is equal to the change of momentum. That's what this means. I'll do some example problems and that'll be done. Example number 1. We have a 2,500 kilogram truck that is stationary and not moving. Then, the engine applies 3,000 newtons of force for 5 seconds. How fast is the truck moving afterwards? So we can answer this by using our formula we just came up with. This relates the change of momentum to an object to the force it experiences. We know the force that the engine provides. We know the amount of time that the force acts. So we know the mass of the truck, which goes here and then also here. And we know that the truck was initially stationary, which means that the initial velocity is 0. It's not moving. So I know there was a lot of arrows, but this tells us everything we need. We plug in the numbers. The only variable we have is the final velocity of the truck, which is great because that's what we want to solve for. So you just do some algebra. You multiply these. Then you divide by 2,500 to get a final velocity of 6 meters per second. Turns out 3,000 newtons is not a lot of force to move a very heavy truck. Even if you apply it for 5 seconds, it won't be going very quickly. Example number 2. A Ferrari 488 GTB car has a mass of 1,565 kilograms. It can go from rest to 27 meters per second in 3 seconds. This is like 60 miles per hour. I looked this up. These are real numbers. So how much force can a Ferrari engine create? Well, we'll look at our formula, which says that force times time equals final momentum minus initial momentum. So we'll just plug in these numbers. It looks like we have the mass of the car, which goes there and there. We know how much time it takes. We know that the car goes from rest, so the initial velocity is 0 to 27 meters per second. So the final velocity is 27. So we can plug in those numbers. The only variable we have is the force, and that's what we want to find. So you just multiply those. That equals 0. It's going to go away. Then you divide by 3. And you get that the force is 14,085 newtons. So this is about how much force a car engine needs to speed it up really quickly. Example number 3. You have a 0.7 kilogram pool cue striking a stationary 0.18 kilogram billiard ball. This is a pool ball, that thing I showed you at the beginning. After being hit, the ball is moving at 3 meters per second. So what is the impulse imparted to the ball? This is our formula. And this is kind of annoying because this says what is the impulse imparted, but I don't see impulse anywhere. That's because actually both sides of this can be used to calculate the impulse. This is the impulse, it's the literal definition. I could also use this to figure out the impulse. So both sides of these are independently the impulse. So I just got to see what the problem gives me, and I can plug the numbers in. So I can solve for either side of this to get the impulse. The problem gives us the information to solve this shouldn't say left, this should say right side, I'm stupid, to solve the right side. Because it gives us the masses and velocities of the billiard ball. So we're going to keep this side and plug in the numbers to get the impulse. Now, this can be a little bit tricky too, because this has mv, and the mass of what? Because we have two masses right here. We have the mass of the pool cue, and then we also have the mass of the pool ball, the billiard ball. And so we have to think a little bit about this problem. It says, what is the impulse imparted to the ball? So we want the change of momentum of the ball, so we're going to use the ball's mass for both of these. This is actually just a trick. It never shows up in this particular equation. It's there to trick you if you don't really know what you're doing. So we'll plug in these numbers. The mass of the ball, the final velocity of the ball, the mass of the ball, the initial velocity of the ball. You can put the numbers into a calculator, and you'll get that the answer is 0.54. This is just the unit, kilogram meter per second. So the impulse imparted to the ball is 0.54. That's the answer. Example number 4. We have a 200 kilogram motorcycle moving at 30 meters per second on the highway. Then the engine turns on, starts applying 500 newtons of force, and it speeds up to a final velocity of 60 meters per second. So how much time did this take? How long did it take the motorcycle to move from 30 to 60? So use our formula. Force times time equals final momentum minus initial momentum. We can plug in these numbers. We know the force. We want to know the time, so that's going to be our variable. The final velocity was 60 meters per second. The initial velocity was 30 meters per second. And we know the mass of the motorcycle, which goes both here and then also here. So we'll plug those numbers in. Time is the only variable, so let's just multiply these out, then subtract them, then divide by 500. And the answer is 12 seconds. That's how long it takes for the motorcycle to go from 30 to 60 meters per second. Example number 5, I think I have 7 of these. We have a 0.3 kilogram dodgeball moving towards a wall at positive 5 meters per second. So it's moving forwards initially. Then it bounces off the wall and heads backwards with a velocity of negative 5 meters per second. So how much impulse did the ball experience during the bounce? We have our formula. Remember, either side of this could be used to calculate the impulse, the left or the right. It looks like it gives us the masses and velocities of the dodgeball, or the mass and velocities of the dodgeball. So it gives us the info for the, once again, right side. I don't know what I was thinking. It gives us this information, so we'll plug stuff in here. The impulse is equal to the mass of the dodgeball times the final velocity of the dodgeball, multiplied by the mass of the dodgeball times the initial velocity. So plug those in. You got to be careful because the final velocity is negative 5 because it's moving backwards. So you solve that. You get negative 1.5 minus 1.5, which is negative 3. So the impulse it experiences is negative 3 kilogram meters per second. You're allowed to have a negative impulse if the force is applied against the motion. So the dodgeball is initially moving this way, But when it hits the wall, the force pushes out that way. So that's why you have a negative impulse, because you had a negative force. Example 6. You have a 0.1 kilogram tennis ball moving at an unknown initial velocity towards a tennis player. The ball hits it with his racket for 0.2 seconds with a force of 20 newtons, and it goes flying away with a final velocity of 4 meters per second. So what was the initial velocity of the tennis ball? We have our formula. We have everything we need except the initial velocity. So let's just plug in the numbers. That is the force, that goes there. That is the time, that goes there. The mass of the tennis ball goes here and here. And it says the final velocity was 4. So you plug in all those numbers. The only variable is the initial velocity. And some people might have trouble solving this right here, because we have this that we multiply, this that we multiply, and then minus 0.1 times the initial velocity. So let me multiply those out. The way that I like to solve these is I like to not have a minus with the variable over here. So I'm going to take this and add it to both sides. So I'm going to take 0.1 times VI, add it to the left and the right, to sort of move it over. Now I'm going to subtract by 4, and then divide by 0.1, to get the answer of negative 36 meters per second. So that was the initial velocity. This might be kind of a tricky algebra problem to solve, but it's just algebra at this point. And it's negative 36 meters per second as the initial velocity of the ball. Last example. 2 people, Alice and Bob, have the same mass, 60 kilograms. They jump out of a building. They're both moving with the same velocity right before they hit the ground, which is 8 meters per second. Alice lands on a trampoline and comes to a complete stop in 1.2 seconds. Bob just lands on the ground and comes to a complete stop in 0.2 seconds. He doesn't bend his legs very well. So who feels more force from the ground as they stop? The person who landed on the trampoline or who landed on the ground? Well, pretty clearly you're going to be able to see that landing on a trampoline is not going to break your leg because you feel less force. But why is that the case? Let me go through the numbers. We have Alice's impulse equation and Bob's impulse equation. Now they both have the same mass, and they're both moving at the same velocity right before they stop. They also come to a complete stop at the end. So when they come to a complete stop, that lets you know that the final velocity is 0. The velocity they're moving at right before they hit the ground is 8, and they have the same mass, both of them, which is 60. The only thing that is different about these two people is the amount of time that it takes to stop. Alice stops slowly on the trampoline. Bob stops quickly on the ground. So this side is going to be the same for both of them. Let me just solve that. That should be negative 480. My bad. So you take this and you divide for Alice by 1.2 and for Bob by 0.2. And you get that Alice's force is negative 4,000 newtons because it's against her direction of motion. And Bob's force is negative 2,400 newtons. So Bob feels way more force. And the only difference in between these two people is the amount of time that it takes. Bob stops quickly, which is why it takes a lot of force to stop him. And Alice stops slowly, which is why she feels less force and doesn't break her leg. That was it. I hope it was helpful.